So I wanted to take a little time this morning and talk about behavior of things with stress concentrators that are subjected to more complex loading. So I'm going to talk about stress and strain concentrations and some ideas about non-proportional loading, and look at states of stress effect on fatigue notch factors, and finally I'll mention a little bit about cracks and notches. So I always like to start in the morning with some little story, so I wanted to tell you one about my family. I was gone on a trip like this, and I got home, of course, and at that time my daughter was, I don't know, maybe four or 5 years old. And so she's glad to see me, I think, but probably not. And and I said, "Oh, why don't you come to the office with me today, and I'll take you to McDonald's for lunch. I just want to go up and check the mail and so on." And well, okay, yeah, chance to go to McDonald's for lunch. And so of course I went, and the graduate students figured out I was in my office, and so the graduate students came to see me, and I talked with them, and a few people called on the phone, and I talked with them. Of course, the 5-year-old is, not as happy as she might be, but I was always prepared because I had colored chalk, and I had coloring books and all these things to entertain my children. So finally, we go to McDonald's, and she's happy, and we go home, and when we get home, her mother asked her, "Oh, what did you do today? You were gone a long time." And 5-year-old, right, said, "Oh, it was really boring, really boring." And then she says, "Well, what was your father doing?" And she goes, "Well, people came to see him and he just talked. And then he just talked on the phone. And that's all he did was talk. And I certainly don't understand why they pay him for that." So this is what a professor does in the eyes of a 5-year-old. And this is a story I've tried to improve on over the years, but I can't. Right? I mean, it's a very good description of what I do. I just talk and I talk and I talk, and people pay me. Yeah. Sometimes I have better things to say than others, but I don't know. So here's a problem we want to look at. It's the last piece, really, of multi-axial fatigue, in that we want to apply what we know to real structures. And this is an easy one to both test and analyze, and representative of many things that one finds in service. So just think about some kind of shaft which is loaded in combinations of, well, here you can see I can load this and bend it in various directions, and I can twist it, and I can also pull on it. And you can think about these as axles on cars or tractors or all kinds of things like that, or some kinds of shafts in transmissions. And these are the real parts that actually have multi-axial fatigue problems. Generally, you do not have multi-axial fatigue problems if you have a plate with a hole in it. And I'll show you why that is. Right? When you get a plate with a hole in it, it's really hard to get multi-axial stresses. It's almost always a uniaxial stress situation. Okay, so we can do this, and we know what our strategy is, because if you think about what we did yesterday, right? So yesterday we said, fine, we have this big blob of material, and we know someplace there will be a critical element, and so I've been drawing that just as a cube, and we have some external loads that act out here, and finally that resolves into stresses in particular directions in this cube when we calculate fatigue life. So the only difference now in going to a structure is I don't know where this cube might be located. You see, if I just have a bar like this, it's pretty obvious where the cube is. And so now we have another level of searching. So I have to search through the structure and find the critical spot. And then once I find the critical spot, then I have to find the critical directions in that spot and how the loads combine. Okay? Well, these are pretty easy to do, of course, because I know that the maximum stresses will exist here someplace around the radius. worth pointing out about the stress concentration factors for these kinds of geometries. And so if I just look up the results, and I have a bar that has a groove on it, and I look at the stress concentration in bending, then for various ratios of the two diameters, of course, as the radius gets very small, the stresses get very high. And I only show you this to show that there's a big difference between the stress concentration factor in bending and torsion. If you could figure out how to make everything in torsion, structures would last a very, very long time. You remember yesterday I was showing you that in torsion alone, the material parts last a very long time because these shear cracks have trouble growing, and the stress concentration factors are lower as well. Right? So all the engineers know about stress concentration factors. So how about we look at what is the stress concentration factor for a simple hole in a plate? 3. How many think 3? You know, it's morning time. You know, we need our morning exercise. You know, that's usually a good answer, but the one I always give is I don't know. And the reason I don't know the stress concentration factor for a hole in a plate is that I don't know how the plate is loaded. So the stress concentration factor for a hole in a plate could be something between 2 and 4, with 3 being the most common. Right? And that's why yesterday I said if you don't know, that's the very best initial guess. Right? It's always the best initial guess for these things. So we can just look at this a minute. And so there's a hole, and I showed this before when this kind of slide before when we looked at a crack. So I put a hole in there, and I load it with the stress in this direction and some stress in the other direction, which is a constant lambda times this one. And okay, there's the hole, and I can look at the stress fields everywhere around that hole. So if you just look at around the edge of the hole, then if you have biaxial tension around the edge of the hole, then the stresses are constant everywhere. Right? So everywhere around the edge of the hole, they're always the same. And of course, you have the stress concentration. Right, the magnitude of these stresses is only twice as high as the nominal stress. And of course, the familiar stress concentration of 3 if this were just loaded in tension, like that. And if I twisted it, then the maximum stresses are here, 4 spots, right? And they're 4 times as big. Right? So I really don't know the stress concentration factors until I know what the loads are. The other thing is, what if I twisted the hole? You know, what if I applied pure torsion to a hole? Okay. And instead of looking at what the tensile stress is here, right, I look at the shear stresses around the edge of the hole. Well, and if you do that, there's the shear stresses around the edge of a hole, which is loaded in torsion. And if you look at the edge, right at the edge, then you'll see that the shear stresses are 0. And they peak up at a distance of about 1.3 times whatever the radius is. Now, why is that important? Well, I'll show you this slide first. Right. If you have a hole in torsion, frequently you get all the cracks to initiate out here. And people say, isn't that strange that the cracks initiate away from the hole? And this is a particularly important problem in rivets and aircrafts. Frequently the cracks initiate not at the edge. And there's a crack here, there's one over there, there's one over there, right? One out here. And if you fatigue test this for a very long time, after a very long time, then you start to nucleate some cracks over here. Right? And those cracks come. I'll bet I can manage to trip over this wire and fall down before the hour is over. This is my prediction. Remember, if I don't get up from this, then the class is dismissed. You are not to help me. Yeah, so these are these principal stress ones, right? the maximum principal stress exists there. Okay, if you look at all of the equations, I just want to go back to two slides to 3 to the picture of the hole. If you look around the edge of the hole like this, then there's a little material element. Let's put this right on the edge. So right here I could have 3 different stresses. I could have what amounts to a hoop stress. I just call that thing sigma theta. So it's the stress in this direction anywhere around the edge of the hole. And then, of course, I can have a radial stress. That's a stress which goes this way. And then I can also have a shear stress at the edge of the hole. And what you find out is, of course, that the radial stress must be 0 at the edge of the hole because it's a free surface. And the shear stress must be 0 at the edge of the hole because it's a free surface. So what you find is no matter how complicated I make the loading for a plate with a hole in it, stresses around the edge of the hole where the cracks circulate are always uniaxial. So it's always a uniaxial fatigue problem. And that's why I say that if you have plate-like structures, plates with holes in them, or things that look like plates with holes in them, it's really not a multi-axial fatigue problem. Maybe the failure location changes, because if you look at the different stresses, right, like this, around the edge of the hole, depending on whether it's loaded in shear tension or biaxial tension, then of course the magnitude of the stresses around the edges of the hole change, and the location of the maximum stress around the hole changes, but the state of stress is simply uniaxial tension. So that means that the real multi-axial fatigue problems come from solid structures. Things like the shafts and things like turbine blades and things that have a lump of mass of some sort. Because there you truly can build up multi-axial stress situations. So if we look at the loading of notches, so I want to look at these 3 cases. First one is I can have uniaxial loading that produces multi-axial stresses at notches. I can have multi-axial loading that produces uniaxial stresses, and that's the one I just talked about. And I can also have multi-axial loading that gives multi-axial stresses as well around notches. And this is the one I showed you yesterday, so I won't take extra time with it, other than to say I have a plate with a hole in it, as before, and I just said you can pretty much ignore multi-axial fatigue when you have structures with plates with holes in it. That's true until the plate with a hole starts to look like a solid. So if I have a really thick plate, suppose I had this plate of 100 millimeters and I made it 50 millimeters thick. That's a solid just like a shaft. That's a solid just like a shaft, unlike a plate with a hole in it that's 5 millimeters thick of these dimensions. So let's look at the other one a little bit, some multi-axial loading that produces uniaxial stresses. And let's just take a bar and we'll just bend it in a couple of axes. And so, let's take a practical situation. Maybe this is the axle on a car or a tractor or something like that. Maybe the axle on my all-terrain vehicle. So you can imagine what happens. So as I am driving about with this vehicle, of course it's going to come up and down like that from the weight. But I'm not a very careful driver, and I am not deterred by small trees and things like that, and so I'm quite happy to run over them. And when I do that, of course, then I will get a big force in this direction as well. So if I look at what's happening to the axles that run in my ATV, it does this for a while sometimes, and sometimes this, and sometimes all kinds of combinations. And so we can kind of look at this and say, okay, let's look at what happens, and just in my very simple idealized example of this, I'll just put the moment in the X direction, and I'll look at a moment in the Y direction, and say, okay, this is the repeating load pattern that I have. And how do these things combine? And yesterday, I gave you all these quizzes about how loads combine to produce different states of stress in my little material element. And today I want to do the same thing, except rather than how the different loads combine to produce stresses in the material element, when we look at a real three-dimensional object, the stresses combine to produce failures in different places. And sometimes two loads damage the same place, sometimes they don't. So if we just look at this, you can see what happens. So in the first one, I have a moment in both of them. In the second one, I have these two moments which are just out of phase with each other, and then I have a moment only in one, and then a moment only in the other. And so if we put that loading history and we put all the geometry into any of the Zeek solvers, this is what would happen. So if we looked at the first case, where it's all, if we look at the first failure location, so think about that I have the shaft and I just mark different locations around the edge of the shaft, and all the loads in the history that I chose were completely reversed in tension and compression. So as I look around the circumference of the shaft, whatever happens at A will also happen at A prime. It will just be at the opposite sign because it's bending. So for this simple example, I know I only have to check 4 locations. Right? So I say, and then before I do this, before I check, I have no idea where this may fail around the circumference of the shaft. So if I look at the loading history at A, the loading history in A will just combine with this magnitude. But remember, what I have is I have a bending in this direction and a bending in that direction as well. And of course, it's a trivial example. You know the answer that those two bending moments will combine off at 45 degrees to produce something that's even larger magnitude. Right? So if I look at that loading history that went through, you can see there's a really big cycle at the beginning and then pretty small cycles after that at point B. And this is what happens at point C at the top, and this is what happens at point D at the bottom, and point D up in that spot at 45 degrees. So if I have a simple shaft like this that I just can bend in 2 axes, then that's pretty easy to analyze. But how about if I had that motor carrier that I showed yesterday? That particular one has 16 load inputs. So how do those 16 loads combine to produce damage in some spot in the structure? And of course the answer is I never know. But the concept is just what I've said here. We just combine all those loads and we do a brute force search to find out what places in the structure see the highest loads. Right? That's all there is to it. So, well, by the way, in this loading scenario, right, if I look at the loads, I can say, that was complex and out of phase and all those kinds of things. That may be in the loads, but from a materials perspective, this is simple, constant, uniaxial loading, isn't it? Because the external loads combine at different places in the structure, and all the places it combines in the structure, each one of those is a uniaxial stress state. If I want to get some idea of I might be able to learn that by the time I finish this. I am trainable, I think. I am willing to be trained. I don't know if I am trainable. Maybe that's a more accurate statement. Okay. Yeah, this is hard for me to press the buttons on this. I'm used to a really big keyboard and so on. And last year, not even a year ago, I got my first smart cell phone, and I couldn't use it. As soon as I started to press a button, random things came up in the neighborhood of where I wanted to press. But I had a solution to this. I had the obvious solution. Right? Get rid of my iPhone and just buy an iPad because the keys are bigger. It was even better, the rest of my family had had iPhones, and none of them had an iPad yet, so I could be a leader in technology amongst my children. Probably the only time. But I can't, yeah. So, well, I have another few hours to try to learn. Okay, you know, a lot of times I am interested in finding the failure locations, and I'd like to find them very quickly. And when I do that, I have very easy things.
Sicuramente le versatilità che sono risultati uguali e misurare.
So yesterday I showed you building my big garden gate and so on and all of my chisels, and I do all that kind of stuff. I wish I could fix all those problems just by pressing a button and so on. You know? What I really wish I could do is I could have a button that would somehow sharpen those chisels for me. That would be ideal. Anyway, if you want to get some idea about where the failure location is, there are some tricks, and this is a trick I told you last time. You know, there's kind of a universal slope to all SN curves, and so if I want to know the relative damage of something, then the easiest and fastest way to do it is to take the ranges, either of stresses or moments, and raise them to the 5th power, and take the 5th root of that, and you get one stress number, and you can compare that at different spots in the structure, and you can quickly find where the most critical spot is, and then focus all your time and attention on just analyzing that one. So let's now look at combined loading. And you know, you can get multi-axial problems, but only as you start to add shear stress. And so if you think about taking a plate with a hole in it and subjecting it now to both tension and shear stress, of course what's going to happen is you're going to produce a maximum stress in some other direction, not the loading direction. And for shear and tension loads equal to one another, then principal stress is almost twice as high before. I show you this slide because I'm going to show it again because it's the quiz question. It's about one of 10 slides in the quiz question. In it, about what happens when you load things in bending and shear. Anybody think of an example where something is loaded in bending and shear, a plate with a hole in it? Wing of an airplane. Wing of an airplane bends. Big engine sits out here. Sometimes does this, and twists a lot, and it bends a lot if it goes through turbulence and twisting and so on. So it is an important load case. All this kind of stuff is simple mechanics. So you know, depending on what the loads are, and that is the combinations of both bending and twisting, you can imagine what's happening is that I'm flying through the sky doing whatever, and does this for a while, and this for a while, and so on. And if I thought about taking the loading history and just taking every load, like this, and the twisting loads and so on, and adding them all up, I would have a very pessimistic estimate of what the life of the airplane would be. And the reason being is that every time it flies, you know, when it's doing this, it is damaging this location around the edge of a rivet hole. And then when it's twisting, right, the loads may be much higher, but it's damaging a different spot. And there aren't as many twisting loads. And then you can think about the other one, well, maybe it's only twisting and it's not bending at all, and that damages yet a third spot. And so what happens in a real structure frequently is damage is distributed around the stress concentrator. Unlike what we do in the lab with little test coupons where all the damage is focused on one spot only. A real structure is distributed everywhere. That's why things can last a long time. We talked yesterday about in-phase and out-of-phase loading and things like that. And here's another example on the same idea, that the damage location just changes with phasing. So I take this plate and I load this and I put two loads in phase, and of course that damages it where I've shown there, and I just change the phasing of the loads, and that changes the magnitude of the stresses here, but it also changes the damage location. So I'll leave that so you that topic with all those examples, and then go on to things that really cause multi-axial stress problems. So a way to get multi-axial stress problems and to get problems that deal with out-of-phase loading is to take these solid structures and introduce shear in some way. And, well, you can see the shaft, so I can take the shaft and I can think about that I have a bending moment in one direction and I now have a torsion that I apply to the shaft. And so I just run a small loading history like I did before, and I think about the stresses in the X direction, the bending stresses, and I can think about the torsion stresses. And of course we know for this geometry, just the bending and torsion, that there will be one spot on here that sees the maximum load because the shear stress is distributed uniformly around the edge. If I wanted to make the problem more complicated, I would just add another bending moment, and then I could distribute the damage everywhere around the circumference of that. But what I'd like to do is to just show you a little bit about how the macroscopic stresses are combining. And so let's look at what happens at time t1, and here's the situation at time t1. I can think about that I have two principal stresses that come from the torsion, and they are here and here. And I have bending at the same time, and so I have a bending stress that acts in that direction. And, well, those are the individual components, so you have to more or less add these vectorially. That's not a true, literally that's not a true statement because you have to account for the differences in area. But let's just think about it, if we're able to visualize this, that we're just going to vectorially add those stresses. And when we do that, we're going to get a big stress out in this direction. And whatever angle that is, looks like about 30 degrees. And now as we proceed to time t2, then we have a little different situation because at time t2, I have simply changed the direction of the torsion. And so when I change the direction of the torsion, again, just to visualize this, I think about more or less vectorially adding these, and you can see I have a big stress component out here. So what's happened is that I have a situation where the principal stress direction starts here and moves over to here. And that also means all the shear stress directions are going to change as well. So what this means is I have one of these out-of-phase loading situations where I'm activating all shear planes between this one and this one. And then finally I get to time t3, and at time t3, now the principal stress direction is just in this direction. So now I'm damaging one plane, but what you see is the magnitude of this is much smaller than the others. And finally at time t4, then I have a situation where I have the two principal stress directions like that, and of course I know where the maximum shear plane is. So if I want to analyze this, this is really a non-proportional loading problem. So after I find the point in the structure, I now have to find which are the planes and directions that have the most fatigue damage. Okay, so now I know what the macroscopic stresses are. And I have to search and find all these locations. So let's say that we can do that. I have another problem now when I deal with real components that we have not talked about yet, and that is the effect of the gradients. So we have this concept of the stress concentration factor, and we know that stress concentration factor, these are the bending and torsion that I had before, and that as I go down with the natural radius, this goes up, and of course if the natural radius is 0, then of course the stresses will be infinite. Right? I have no problem with an infinite stress in the structure. Oh, why not? The infinite stress acts over a length of 0, doesn't it? So how can an infinite stress acting over a length of 0 be damaging? If it's acting over a length of 0. It's a problem, isn't it? So if we think about a real material has some kind of crystal structure, and we have to have a concept that, you know, a stress has to act over some volume of material, right? So material scientists always talk about this as the process zone of the material, right? It's that stress which is important, not this infinite stress which acts over zero length. Well, we can take that same concept, and this is for both torsion and bending. Let me just talk about some real data. So, okay, I take these two structures, middle diameter is the same. I run a bunch of tests on this one, and here is all of the fatigue data. And I do all the theory of elasticity correct, and I calculate what the stresses are here, and the stresses here turn out to be 3 times the average stress. So that means if I wanted to apply fatigue theories, what should happen is I should take all of this materials data here, and then I should divide this by 3. And that should be a very good estimate of what this does, because that would put the same stresses there. And if I do that, this is the line you get by dividing it by 3. And then you go into the lab, and after going into the lab, you say, oh, what do the real experiments do? And you can say, wow, this is pretty good. Look, I was expecting at this stress level to have a life way back here of about 100,000 cycles, and in fact, I could go 10 or 100 million. Pretty significant error, isn't it? You say, wow, you know, this maximum stress is not what's really important, right? The effective stress concentration, right, is only about 2. It's only about 2, right? The 30% difference, right? And 30% lower. You know, almost everything people do in fatigue reduces the design stress. So things are bigger, heavier, and so on. But here's something that says, wow, maybe you can use higher stresses than you think. So let's look at this effect, and this is the so-called gradient effect in fatigue. And I like to explain escape.
Escape.
Yes. Maybe. You know, just because I got lucky once knowing what to do again, doesn't mean I'll do it again, but maybe. Maybe. People have looked at this, people have looked at all of these gradient things for a long time, probably for more than 100 years. And there are a couple of famous pieces of work. One of them is by the German Neuber. And Neuber actually was a mathematician. And he has many of the stress concentration factors that we use today come from his work. And I always assign his papers to my students to read because they are incomprehensible. Yeah, they're filled full of elliptical coordinates and so on, and then at the end pops out the answer. And of course we are only interested in the answer. But he also was interested in these gradients, and he explained things as follows. And he had a concept of a mosaic block size, is what he called it. And he said it's some kind of material process zone. But he was a mathematician, not a material scientist, so he didn't associate it with any specific material dimension. I always like to do that, even though it's not correct. Because the material dimension is not the grain size. But I like to use these individual crystal sizes just for illustration, because it just helps us understand it a little better. So imagine now that I have this circumferential notch, and of course here's just the outside geometry that we looked at. And I think about what the stresses are. And so I have all of my stress analysis. And of course, here is the stress field. As we go away from the notch, the stresses become lower. And when I had the previous slide there, that stress that we calculated, 3 times the average stress, that's the swing way up here. And I'll just say that that's the stress that's coming from KT. And now I superimpose that stress onto the microstructure. And so I've drawn a little microstructure here of these individual little grains here, right? And think about this now as the process zone, right? If that's the process zone, what stress acts in the process zone? Well, it's not really the maximum stress. If I think about from a material science viewpoint, if I have an individual crystal in the material, an individual crystal in a material cannot support a stress gradient. Because I reach the shear stress, critical shear stress, and as soon as I reach it, that crystal shears. Dislocation runs from somewhere in the middle out to the entire edge. All right, so you can have this concept that materials will have constant stresses over this process zone. And like I say, I like to use the grain size as the process zone because it's something I see in a microscope, even though it's not quite the right dimension. So this idea of the fatigue notch factor, Kf, in the previous slide says, okay, I want this average stress here, and this average stress here might only be 2 times the nominal stress, and that's the effective stress concentration in fatigue. Okay, so that's the idea that's behind this. And what would happen if I made things smaller? If I made things smaller, I just make this geometrically smaller. Right? And I look at the stress field. When I look at the stress field for making this smaller, then I essentially move the stress field in this direction. And now I apply the same arguments. I want to test something that has the same stress concentration. Right? I realize that in a real structure, it's not, we don't think in terms of stress concentration factors, but think about this as the calculated surface stress in a finite element model of something that's a little bit smaller. And when we do that, then I look at the same material, so the microstructure size hasn't changed. Right? This process zone size has not changed. And so now I look at this and say, okay, look, this was the maximum stress, right? But in the process zone, my best estimate of the process zone is the average stress that comes from the stress distribution in the elastic solution, and of course this average stress is lower than that one. Okay? And what that does is that lets us at least make sense of, classic experiments. Suppose I took this plate, big plate like this, and I took it in the lab and I put in different size holes. Finally, one down there you couldn't see. And I analyzed this, right, for all the stresses. And so if I analyze this for all the stresses, then the stress at the edge of this hole, this hole, this hole, this one, and this one would all be the same, because they're all round holes in this plate. Right? But there isn't anybody in this room who thinks the failure would occur from the smallest hole. Right? Everybody would guess this one, and that would be probably what happens almost all the time. Maybe this one once in a while. Once in a while things just go wrong in the lab, but almost everyone would guess this, and this is what would happen in the lab. And this is the reason. Right? I have high stresses that are at the edge of this hole, but they act over a very small length. And that length might be much smaller than the material process zone. So in fact, I could make a hole small enough that it would have absolutely no effect in fatigue. Right? Any guesses what that means? How small is small in numbers? So what is the size of a crystal in a piece of low carbon steel? What is the size of this?
20 micrometer.
How much?
20 micrometer.
20.
20.
Yeah. So if I had a hole that was smaller than that, probably have no effect. Probably have no effect. And there are people who do this. Professor Murakami has done this since he's been a graduate student. Drills very small holes and runs fatigue tests. And you find out someplace between 10 and 100 microns, depending on what the material is, will have absolutely no effect in fatigue. Absolutely no effect. Yeah. Pretty nice. You know how to drill a hole, a very tiny hole? Pretty clever the way he does it. Because they have very high-speed little drill press, and you have a very small drill, so you can actually drill those size holes. Of course, if you've been in the lab and you try to drill a hole, you know the technique. You put in there, you pull down the handle and all these things. And the way they do that is they simply pass an electric current through the specimen. And when the drill touches the specimen, a little light comes on. And as soon as they see the light, the graduate students just stop immediately. And they say, okay, I have a little hole now. And then they go over to the microscope and see how well they did. And it's pretty clever. Okay, so you have the idea of what happens. Now let's look at this, and I said the size of this thing, which would be non-damaging, is on the order of maybe 10 to 100 microns. Let's look at the effect of the materials with this. So if you have a lower strength steel, piece of carbon steel, this is the diagram that I used before. And now let's have the same plate that's here and make it out of a really high strength piece of steel. What will happen? Well, what will happen in a high strength steel, let's say, is I'll have all the same stress gradients, except the microstructure will get really small. That's how we make high strength things. Strength and microstructure size just go together. And so, okay, I make the same arguments. I say, well, look, what is the stress that acts in this little process zone? Well, the stress that's acting in this process zone is much higher than this one. So if I go back to my experiments now, right, my thought experiments, and let's look at what might happen. Right? Of course, I don't have a good size scale here because I can't draw a 10 micron hole down here, but let me talk about it as if I did. Maybe in the low strength material, both of these holes are big enough to have really high stresses in this process zone, and maybe these down here, these are small enough that the stresses are pretty low. So if I really went into the lab, maybe the majority of the failures would come from this one, but every now and then you'd get some from this one. Okay? And never from these. My stresses are just not high enough. And now I do another set of experiments. I take this same plate, or many of these same plates, and I make it out of a really high strength material. Now if I make it out of a really high strength material, the stresses are high for all of them. Because now maybe this one is big enough such that the stresses in the process zone are really, really high. Because the length scale is small. Right? I'm only interested in stresses up near the edge. Right? And the stresses up near the edge of all of these now are the same. So that's the idea behind gradient effects. And you can do other things about changing the shape. What you tend to find is that if you put something with a higher value of the stress concentration factor, Kt, then there's always a sharper stress gradient. That's the reason that the stresses are high here. And there's a much bigger difference between the Kt and the Ki. And I would say, you know, this approach has been around for, I don't know, maybe 100 years people have been doing that. And it's completely empirical. There are other ways to look at it. And what's implemented in much of the software are things looking at a critical distance. Because if I go back through the past 3 slides, I won't do that. But what I showed you is I showed you a reduction in the stress that acts on this critical element size. But it really has to do with the length. Right? It's really this stress is acting over some length. So let's take these holes with plate with a hole in it with different diameters and just look at the stress gradients now. Right? So suppose this is whatever I wrote. So suppose this is the 10 millimeter hole and this is a 1 millimeter hole and that's a 1/10 of a millimeter hole. So you can look and see what happens is, right, I have to have a certain size and maybe my microstructure size requires that microstructure is maybe a millimeter. Right? Really low strength material. And so maybe the process zone might be half of that. So let's just say 1/2 millimeter. And let's just look now at the distance from the edges of these holes. What are the different stresses at a 1/2 millimeter? And what you can see, you say, well, actually they're still really high. The top one, and they're only half as much as I go here. And if I put in the very smallest one, right, there's no stress concentration at all. So if I wanted to do an analysis, one of the easy things to do would say, fine, I have all of my numerical analysis. Let's simply not ever look at what happens on the surface. I want to look at what happens a little bit below the surface, a little bit subsurface. Right? And in fact, that's what people who do the calculations really do. We rarely look directly on the surface because we know these gradient effects are important, particularly for smaller things. So we'll use a subsurface stress. And the idea is we want the stress in this process zone. And there's putting these two concepts together. So there maybe was my material size, and I want the average stress in the middle, and so I will take half of that distance and use it in the calculations. Other people still like to use these fatigue notch factors. It's kind of interesting. People have been developing these empirical fatigue notch factors. There's one of the formulas. This formulation is due to Peterson. Neuber's formulation looks the same, except it uses the square root here instead of linear function. It's the effective stress concentration is 1 plus kT minus 1 plus A over R, and A is this mosaic block size. Okay? And if you try this in bending, since the people have been doing it for 100 years, you can see there's a pretty reasonable correlation between this calculated KF and the experimental KF. By the way, that must happen. Why must it happen? It's an empirical theory. All I'm doing is showing how well I fit the data. You know, we take all the data, we plot it. By the way, I recommend doing that. Not enough people take their theories afterwards and plot it and see if it reproduces the original data. Just as an aside, that's one of the critical things to do in all of these plasticity equations, is to say I have these plasticity equations, I take the strains as an input, and then I might use my plasticity models to tell me what the stresses are. And if you want to check your model and you have a good model, you should be able to take those stresses, put it back into your model formulation, and see if you get out the input strains. You will be surprised how many models that doesn't work. You will be very surprised at how many. Okay, anyway, so that's what happens in bending. If you take the same shafts and do it in torsion and apply all these little empirical rules for what happens, you can see in torsion correlation is not all that great. But people still use it because they say, well, it's just fine. At least it's on the conservative side, so I won't get in trouble. A good idea or not? So I was at a conference about high temperature fatigue some years ago, and there was this young man from Shell Oil, and he did some experiments, and he was comparing some different theories about high temperature fatigue and so on. And of course it became question time, and one of the academics whose name was on one of the theories, not me because I didn't do high temperature work, so I'm in the clear here, asked him, well, what do you guys really use in design? And the young man said, oh, we use such and such a theory, and it was the one that had the worst correlation in the plots. Okay? And of course the academic, well, how can you do this, and it's not based on the physics and so on. And this very calm young man said, do you realize how much money it costs for us to get a broken drill out of a hole in the ground that's 5 miles deep? We're never ever going to use a theory that has a chance of a non-conservative result. We don't care if it's right. We just want to be sure you don't get in trouble. And this is the difference between us academics and scientists, right, and the engineers. The engineers, right, want to first and foremost make sure they don't get in trouble. So a lot of people use these things, right? A lot of people use these things. Like I say, if you twist something in torsion, it's really good. Right? Figure out how to make everything as twisting in torsion. Okay. Why does that happen? Right? Why do things just last so long in torsion? And here's the reason. Right? We can either look at something that has a step shaft like this, or we can look at something that has a groove around the edge. And okay, I have my view of fatigue, and I have my calculations, and I calculate what happens at the root of the notch there, or I can calculate what happens here. And if it's a long life fatigue problem, then I showed you yesterday that these are these spiral cracks. But what happens when you start to get these long life spiral cracks in this situation? The cracks grow out of the stress concentrator. Of course, if the cracks grow out of the stress concentrator, they're not going to go very fast at all. And the lives are really, really long. That doesn't happen in tension. Right? That's why tension is the dominant failure mode everybody is really concerned about, because if I had these same geometries in either tension or bending, all the crack growth would be through the thickness trying to break it. you wouldn't have these scenarios where the cracks try to grow out of this and grow along here. And here you can see how this is spiral, right? The crack starts there and then goes way outside the stress concentrator and spends a long time growing in a low stress zone. Okay, that's what happens. How about the mechanics behind these things? We want to do calculations because we want to know what are the real stresses and strains. And almost all the calculations that are done are all done on an elastic basis. So let's again come back to my plate here and suppose I want to know what are the real stresses and strains here, including the plastic deformation that might be there. And I only have the elastic solution. So I know what is the elastic solution, so I apply some nominal stress here. And I say only the elastic solution, so let's say I'm just going to do a finite element model. So I do an elastic finite element model of however complicated a shape you like. And I want to know what kind of plasticity I might expect to find in the zones around here. And to do that, we do something very simple, which is called Neuber's rule. So as I mentioned, Neuber was a mathematician, and there's a famous paper that's derived in elliptical coordinates of a beam in axisymmetric shear. And what that means is it's a beam that looks like this in cross-section. So you can see what it looks like, and it's loaded in shear like this. Okay, that was the test problem. And Neuber said in his paper, right, 7 or 8 pages full of incomprehensible mathematics, and he derived the solution for an arbitrary material law. So presumably all real materials are a subset of his derivation, since you derive it for an arbitrary material law. So there's no problem having a stress strain curve in Neuber's derivation that looks like that. Pretty much like a real material. Right, that was pretty good. He derived all the mathematics, and at the end he said, this may prove useful. And he wrote down that the real stress concentration factor is equal to the geometric average of the stress and strain concentration factor. And that's what he wrote. Right? I've simplified those 7 or 8 pages of mathematics into this one formula up here. What it said really was, if you look at the elastic solution for stress and strain, and I wrote this as kT times the nominal stress in this mechanics, strength of materials approach, but this could just be the elastic stress that comes from the finite element model as well. The product of the elastic stress you calculate times the elastic strain you calculate is equal to the product of the real stress and the real strain. And that turns out to be very, very powerful. And, well, since it's an elastic model, stresses are calculated with elastic assumptions. And so I have this elastically calculated stress and strain are equal to the real stress and strain. And then we say, well, for cyclic loading, I just replace the stresses by the stress ranges and the strains by the strain range. So, but the idea is the product of the solution is the product of the elastic solution is equal to the product of the real solution. So let's just look at that. So I have a material stress strain curve, and so that's shown in blue, and I have a solution way up here, because of course when I do an elastic solution it doesn't plastically deform, and so I calculate stresses which are too high, and I calculate strains which are too low. And so I've calculated the solution here elastically. And of course I know the real solution must lie somewhere along this curve, because that's the real material response. And where does it lie along that curve? Well, if you look at this, this is essentially an energy argument, because if I put 1/2 out in front of both sides, I get the energy. So you can essentially say that this area, right, is equal to this area. And of course, for this, I've exaggerated this a lot. The normal plastic strains we deal with are way down here, and so using this method you get a very good approximation of the energy that's under the stress strain curve. And so that's why it works. And people have been using that for uniaxial fatigue for the last, I don't know, 30 or 40 years. There are some other rules where people actually calculate the strain energy and they worry about the shape of the stress strain curve and so on. It gives a slightly